Very good morning to all of you. The next topic for this course is to learn interpolation techniques. When we have been given a set of points given by in terms of tables like x and y, x naught, x1, x2, and so on, xn, and you have corresponding values at these nodes are y0, y1, y2, and so on, yn. So this first row is called the set of nodes, okay, and the second row is called here the ordinates. And we wish to find a smooth curve which passes through the given data set of points. Okay, so we are interested in finding a polynomial, say p of x, of lowest degree. Okay, so you have been given with a data set of n plus 1 point. So we are interested in finding a polynomial of lowest degree at most n, such that p of xi is equals to yi, and the above data set may be is given for a function called, let's say, f of x, and we wish to interpolate f by a polynomial. So this condition, so here I is running from 1 to n. So this condition is called interpolating condition. So this condition is called interpolating condition. Okay, so interpolating condition. Okay, so with this idea we are going to proceed further. So what are the outline for this unit is we are going to learn some basic interpolation technique and corresponding error analysis for it. Okay, right. So one example for motivation point of view is here. So you have been given with a set of points, okay, which is obtained by an experiment, okay, and which gives you the viscosity of water at different temperature. Okay, now from the above table, how can we estimate a reasonable value for the viscosity at temperature 8 degree? Okay, so 8 degree is not in the table, so you need to identify a interpolating polynomial of lowest degree which interpolates the given data with less number of error. Okay, so this is the idea for giving the answer for this problem. Okay, right. So we are given a table of n plus 1 data points, let's say. So we have been assumed that this data set is for a function f of x. So f of x is a curve, smooth curve. Okay, and we are again and again talking that we are going to interpolate by a polynomial. So that is due to the Weierstrass approximation theorem. So we have Weierstrass approximation theorem tells you that a continuous function can be approximated by a polynomial. Okay, right. So we are given a table of following n plus 1 data points. So what is our problem? So what the first problem is, whether is it possible to find a polynomial p of lowest degree for which the interpolating condition matches. P of xi is equals to yi. Okay, if it is so, let's suppose the problem 1 is solved. Then if problem 1 is solved, whether it represents the data approximately, means whether it really approximate the function itself, and if possible whether it filters out the errors. If it is so, means suppose the second problem is also resolved, then the third problem is it possible to find a function g that is simpler to evaluate and produces a reasonable approximation method. So we try to answer these all three problems. Okay, right. So let's move further. So let's suppose you have been given with a data set of n plus 1 points, right? So let's have n equals to 0. Okay, so means you are given with a one data set. So what will be the possible interpolating polynomial of lowest degree for the given data set? So with a given point, what you can have is, so if I wish to write the interpolating polynomial for a given data set, that will be the constant polynomial p of x equals to y naught for all x. So this satisfies the interpolating condition, p of x naught is y naught, right? Right, so this satisfies the interpolating condition, and this is a polynomial of degree 0. Okay, so if you given with this data set, suppose you have been given with the data set, one more additional point is given to you, x naught, y naught, and let's say x1 and y1. So what will be, so let's previously denoted 0 here. Okay, so that it denotes the 0 degree polynomial. Now what we are going to here, so let's say p1 of x for n equals to here 1. So we wish to interpolate the following data set. Okay, and we are going to, let's suppose I am going to use the previous here, so it's equals to, let's say p0 of x, it should interpolate, plus some c time, so it should use the complete data set, right? So x minus x naught. Why I have chosen this as c is some non-zero number. Okay, c is some non-zero number that needs to be determined. Okay, now if you see, p1 of x naught is p naught of x naught, and that is equals to y naught, because x naught minus x naught is 0. Okay, right. What another thing is, it should matches at x1 as well. So p1 x1 must be equals to y1. The other interpolating condition is this. So once you have this implies, so p naught of x is y naught plus c time x1 minus x naught is equals to y1. Now this equation is solvable. Okay, so we need to determine c such that this condition satisfies. Okay, so what we require is these x1 minus x naught need to be non-zero. Means x0 and x1 should be distinct. Okay, so you should consider you are adding a distinct a set of points where x0 is distinct, x0 is not equals to x1, distinct from x1. Okay, so this above equation can be solved, and if x1 is not equals to x0, then c is equals to y1 minus y0 divided by x1 minus x0, right? C is equals to y1 minus y0 divided by x1 minus x0. right? Similarly, you can proceed in the similar way. Okay, so if you add one more point here, xy, x0, x1, x2, this is y0, y1, y2. Okay, let's say that the third case. So for n equals to 2. Okay, so 3 given points. So you are going to P3 of x, P2, right? P2 of x for n equals to 2. That is equals to, I am going to use the previous P1 of x plus c time x previous at the previous points. So x0 and x1, x minus x0 time x minus x1. Now note that P2 of x0 is equals to P1 of x0, and that is already y0. Similarly, P2 of x1 is equals to P1 of x1, and P1 of x1 is y1. So two interpolating conditions are satisfied. The third interpolating condition is P2 of x2 is equals to P1 of x2 plus c time x2 minus x0 time x2 minus x1. So this equation is solvable for C only if, so here again and put if x1 not equals to x2 not equals to x0. So they all are distinct. Then you can further, then you can get this C. C is equals to, so P2 of x2 is y2 minus P1 of x2 divided by x2 minus x0 time x2 minus x1, right, and so on. So in this way you are constructing an interpolating polynomial of lowest degree. Okay, now note that P0 of x is a polynomial of degree 0. P1 of x is clearly is a polynomial of at most of degree at most 1. Okay, degree at most 1, because if y1 and y0 may or may not be equal. Okay, similarly the P2 is a polynomial of degree at most 2. Okay, and so on. So right, so in this way you can derive the interpolating polynomial of degree at most n. So you have been given with a data set x, y, x0, x1, x2 and so on, xn, y0, y1, y2, yn. So if I recall, so suppose so a result, so if I wish to use the method of mathematical induction, so result is already true for n equals to 0, n equals to 1, n equals to 2. So select let you have pk minus 1 of x is an interpolating polynomial of degree at most k minus 1. Okay, then we define pk of x is equals to pk minus 1 of x plus c time. So you are going to add, you are going to use the points x0 to xk minus. Okay, so here you are going to use x minus x0 to x minus x1 and so on, x minus xk minus 2. Then you will obtain x minus k minus 1. Right. Okay. Right. So by using the points x naught to xk minus 1. Now note that pk of xi is equals to pk minus 1 of xi whenever 1 less than equals to I less than equals to k minus 1. So that is further equals to yi. Okay. So k minus 1 interpolating conditions are satisfied. So this I is starting from 0, right? X naught to xk minus 1. Okay. Right. Now what about at xk? So this c needs to be chosen. This c needs to be chosen so that it should satisfy the last condition that pk of xk is xk is yk. So pk of xk is equals to yk. If you recall, if I will follow the similar pattern, that will give you c is equals to yk minus pk minus 1 xk divided by xk minus x naught to xk minus xk minus 1. This is only possible provided x naught, x1 and so on xk are all distinct values. So these polynomials what we have derived, okay, these polynomials are called Newton's interpolating polynomial. So I wish to write here the derived polynomials interpolating polynomials, okay, the derived interpolating polynomials are called Newton interpolating polynomials. Okay. So this gives you the existence of interpolating polynomials. Okay. So this actually also gives you the existence of interpolating polynomials satisfying the interpolating conditions. Okay. Now what so we have the following results, that if x naught, x1, x2, xn are distinct real numbers, then for arbitrary values, so y naught to yn, there is a unique polynomial Pn of degree at most n satisfying interpolating condition. Okay, right. So we have been given already an existence of such a polynomial of degree at most n in Newton's form. Now the next is uniqueness. Okay, so for the uniqueness, if I wish to prove the uniqueness here, uniqueness is very easy. So let Pn and Qn are two interpolating polynomials of degree at most n such that you have Pn of xi is equals to yi, and Qn of xi is equals to also yi, for 1 less than equals to I, 0 less than equals to I, less than equals to n. Now let Rn, defining Rn of x is equals to Pn minus Qn of x. So difference of two functions, how would you define is, that is equals to Pn of x minus Qn of x. Now clearly Rn is a polynomial of degree at most n. Now Rn of xi, if you call, that is equals to Pn of xi minus Qn of xi, and that both are matches yi and yi, so that is equals to 0 for all 0 less than equals to I, less than equals to. So this implies Rn has n plus 1 zeros. So which is only possible if Rn is a zero polynomial. So this is implies Pn of x is equals to Qn of x for all x. Okay, so this gives you guarantee that if you are trying to identify an interpolating polynomial for the given set of points x0 to xn which are distinct, okay, then there is a unique such polynomial of degree at most n. Okay, so next we are going to learn the Lagrange form of interpolating polynomial. Okay, right. Okay, so before going, let us should not miss the fact that we can actually go for polynomial basis. Means you have a polynomial, so basis is 1 comma x square comma x cube and so on x to the power n. You are going to obtain an interpolating polynomial of degree n by using this basis. Okay, so you can actually go for polynomial Pn of x is equals to summation j equals to 0 to n Cj x to the power j, such that it satisfies the interpolating condition. What is that? Is Pn of xi is equals to yi. So 0 less than equals to I, less than equals to n. So you have n plus 1 equations in n plus 1 unknowns. Okay, and let if x0 to xn are distinct points, then you can show that can be solved uniquely. Okay, so if you try to write in terms of matrix form, so if you wish to write the interpolating conditions Pn of xi is equals to yi for the given polynomial basis, what you will obtain in the following matrix representation: 1 x0, x0 square and so on x0 to the power n, 1 x1, x1 square and so on x1 to the power n, and so on. You have 1 xn, xn square and so on xn to the power n time c0, c1 and so on cn is equals to y0, y1 and so on yn. Right. So if you have x0, x1 and so on xn are distinct, then this system has unique solution, because the matrix, the coefficient matrix, is a non-singular matrix, right? However, if you are going for higher degree, and due to the nature of the higher degree polynomials, they are oscillate widely, okay? So because if you recall the fundamental theorem of algebra, so if you have a polynomial of degree n, is not preferred for interpolating a data set of points, okay, right? So this matrix is called, the coefficient matrix is also named as Vandermonde matrix. Vandermonde matrix, which is ill conditioned, highly sensitive with respect to the data. Okay, right. So the interpolation condition is implies the following, that's already shown. So is the polynomial, again, is the polynomial basis forms a good basis for numerical work? So if you try to plot P1, so you can say x square, x cube, x power 4, x power 5, x power 6, and so on. So if you go for higher degree, it will not, the columns are linearly dependent, columns becomes nearly linearly dependent due to it. So you are not able to distinguish, so there is no you may not be able to make any difference for higher degree polynomials, okay, right? So therefore they have not been preferred, right? So for distinct node, Vandermonde matrix is singular. It is often ill conditioned as n increases, that already explained. The columns of the Vandermonde matrix becomes nearly linearly dependent for large n, that already mentioned. Higher degree polynomials often oscillate widely and are highly sensitive to small changes in the data. So that already explained by using the fundamental theorem of algebra, right? So now, as noted from the result, that there is a unique interpolating polynomial. However, there may be different representation of the same polynomial. Okay, so the another interpolating polynomial which we are going to learn is Lagrange form of interpolating polynomial. Okay, so what it gives you, the polynomial which is at most degree n by using the data set of points n plus 1, that's the same data set here, okay, which is going to represent the polynomial in the following form: y naught L naught of x plus y1 L1 of x plus y2 L2 of x and so on, plus yn ln of x. So this, if you wish to write in a compact form, that is summation j equals to 0 to n yj Lj of x. Now note that y0 to yn, y0, y1, y2, yn are the ordinates, and so here where Li or Lj of x, okay, are polynomials of degree at most n and depends only on nodes, and it depends only on nodes, means x0 to xn. Moreover, So with this means this is independent of ordinates, means y0, y1, y2, yn. So they are independent choice of they are independent from the choice of y's. Okay, so what we can here is, so we can choose, so here, so clearly L j of x are independent are independent of yj's, y0, y1 and so on yn. They are independent of y0 to yn. Okay, so therefore let so the above relation, so you can say then, so this if we call 1, then above equation 1 will also hold true. What we can here is, so we can choose, so here, so clearly L j of x are independent are independent of yj's, y0, y1 and so on yn. They are independent of y0 to yn. Okay, further Pn of xk is equals to summation j equals to 0 to n yj lj xk. Okay, now note that this lj of x, these are independent of ordinates. So these ordinates could be 0 for all j's. Okay, so what we can here, so since okay, so since lj are independent of y0, y1 and so on yn, therefore y0 to yn could also take the following values: yj is equals to delta ij, which you are already aware that is equals to 1 if I is equals to j and 0 if I is not equals to j. So therefore from the interpolating condition yk is equals to Pnxk. So yk is delta ik, that is equals to Pn of xk, and that is equals to, if you summation j equals to 0 to n, yj is delta ij lj xk, if you recall from the previous slide. So that is equals to lix. So this is one of the property of the polynomials L0, L1, L2. So this is true for 0 less than equals to I less than equals to N. So these polynomials, what we are deriving, are called cardinal functions. So this L0, L1, L2 to Ln are called cardinal functions. Okay, so what we have observed just now is, the cardinal function satisfies the following: Lixj is equals to delta ij, means that is equals to 1 if I is equals to j, and 0 if I is not equals to j. So if you use the following condition for the cardinal function, so clearly for, let's say, I equals to 0. So it's clearly L0 of xi is equals to 0 for all I1 less than equals to I less than equals to n. And L0 is a polynomial of degree n. So therefore, this must be L0 of x must be c time x minus x1 and so on x minus xn. Now, for here is z, okay, right? So L0 of x is, if I wish to recollect, was c time x minus x1 to x minus xn. Now L0 of x0 equals to 1. This implies c is equals to 1 upon x0 minus x1 and on x0 minus xn in the product. So therefore this implies L0 of x is equals to x minus x1 to x minus xn divided by x0 minus x1 to x0 minus xn. So if you wish to write in the compact form, that is equals to product of, if I use this symbol as product of j equals to 1 to n x minus xj divided by x0 minus xj. So by the similar reasoning, you can also go for finding the other cardinal functions. Okay, so by the similar reasoning, you can go for finding Lk of x, that is going to be product of j equals to 0 to n j not equals to k x minus xj divided by xk minus xj. So by the similar reasoning, you can obtain the following cardinal function. Okay, now interpolating conditions. So if you recall, interpolating conditions are Pn of xi is equals to, so that is yi. So if you recall, if you recall the properties of the cardinal functions, and if you write it in the matrix representation form, 0 less than equals to I less than equals to n. So the first row is L0 of x0, L0 of x1 and so on L0 of xn. I think L1 of x0 to Ln of x0, C0, C1 and so on Cn is equals to y0, y1, yn. The second row is L0 x1, L0 L1 x1 and so on Ln x1, and so on. The last row is ln x1 x l0 xn l1 xn and so on ln xn. And if you incorporate the properties of the cardinal function, what you will get is the coefficient matrix will reduce to the identity matrix. Okay, right. So they are easy to solve for C0 to Cn, irrespective of the polynomial basis. If you recall the polynomial basis, you have got an ill-conditioned matrix there. Okay, right. So what we have observed just now is the Lagrange's method will express the interpolating polynomial in the following form: P is equals to this. So clearly the polynomials depends only on the nodes but not on the ordinates. Okay. So one can deduce the following formula for the cardinal function that already we have derived. And the interpolating condition P of xi equals to yi for 0 to n implies the following. So where you have seen this coefficient matrix is reduced to the identity matrix. Okay, right. So these are here C0, C1, Cn. Okay, right. So the coefficient matrix reduces to the identity matrix here C0, C1 and so on Cn. Okay, right. So let's take an example that what are the cardinal for Lagrange polynomial interpolation. So what are the cardinal functions and Lagrange form of the interpolating polynomial for the following data? Okay, so you have been given with x0, x1, x2, x3. So 4 data set points, so you are going to get a polynomial of degree at most 3. Okay, so if you so the first row is of xi's and the second row is of corresponding yi's. Okay, now so if I wish to write the cardinal function as 0, that is equals to x minus x1, x minus x2, x minus x3 divided by x0 minus x1, x0 minus x2, x0 minus x3. Now incorporate the values of xi's. So this is equals to x minus x1 is minus 7, so x plus 7 time x minus x2 is minus 6, so x plus 6 time x divide by x0 minus x1, so 5 minus minus 7, so 12 into x0 minus x2, so 5 minus minus 6 is 5 plus 6 is 11 into x0 minus x3, that is 5. So this is your L0 of x. Similarly, you have L1 of x is equals to, you are going to start with x0, you are going to skip with x1, right, factor, so x minus x2, x minus x3 divide by, now replace x by x1 in above, right, x1 minus x0, x1 minus x2, x1 minus x3. So that is equals to x minus x0 is x minus 5 time x minus minus 6, so x plus 6 time x divide by, so minus 7 minus 5 is minus 12 time x1 minus x2, so minus 7 minus minus plus 6, so minus 7 plus 6 is minus 1 time minus 7. Similarly, you can go for L2. Okay, similarly you can go for L2 of x. Okay, similarly you can go for L2 of x. So if I collect all the things, so L0 of x will be here. You can match L1 of x will be this, okay, 12 into 1 into 7, right, 84. Similarly, L2 and L3. So if I wish to give you a hint, so if you recall, the cardinal function is Li x is equals to product of x minus xj, j equals to 0 to n, divide by xi minus xj. Certainly j is not equals to I. Okay, so these are, so this is 1, 0 less than equals to I, less than equals to n. So with this definition, you can identify what are the cardinal functions, and then you can write the Lagrange form in the y naught. So you can the Lagrange form of interpolating polynomial is 1 time L naught of x minus 23 time L1 of x minus 54 time L2 of x minus 9554 time L3 of x. So this will be the Lagrange form of the interpolating polynomial for the given data. Okay, right. Okay, then again, if you go back and look at the Newton method, okay, if you look at the Newton's method, so this is the compact form of the Newton's interpolating polynomial. So if you recall that Pn of x, the Newton form of interpolating polynomial is C0 plus C1 x minus x naught plus C2 x minus x naught into x minus x1 plus C3 x minus x naught time x minus x1 time x minus x2 and so on, plus Cn x minus x naught x minus x1 and so on, x minus xn minus 1. And if you wish to write in the compact form, so this is here is given. Okay, so this is C0 plus, so if you write here I equals to 0 to j minus 1. So you can further write it in the following form. This is a summation j equals to 0 to k, Cj product of I equals to 0 to j minus 1, x minus xi, I equals to 0 to. Okay, now further, so if you write in the following form, so here when you put j equals to 0, so the product is I equals to 0 to minus 1. So here we should use the convention that, okay, product of I equals to 0 to m, whenever m is less than 0, that is equals to 1. Okay, or you can use the, so here you can use the convention. Okay, so the convention is product of I equals to 0 to m x minus xi is equals to 1 if m is less than 0. Okay, otherwise you can use the following compact form of the interpolating polynomial, right? Okay, now also we have also derived the formula for ck, right? By using the pk minus 1 we have derived the polynomial of degree k, and then by using the interpolating condition we have derived the constant ck. So we have all, here we are assuming that the nodes are distinct. Okay, right. So interpolating condition, if you wish to write, that is going to be given. So first condition is P0, right? The first condition is given by P0x. P0x. Then the second is P0, this is P0, this is P1, then P2, and so on, this is Pn. Okay, right? So if you see, this is a lower triangular matrix. So coefficient matrix is a lower triangular matrix. So you can use the forward substitution method to solve this. So if you solve, so this is easy to solve, right? This is C naught is equals to f of x naught. The second equation is C0 plus x1 minus x naught times C1 is equals to f of x1. If you use the value of C naught, f of x naught, so this will give you C1 is equals to f of x1 minus f of x naught divided by x1 minus x naught. So now C naught is depending clearly on x naught only. C1 is depending on x1 and x naught. So if you go further, then you will realize that C2 is depending on x naught and x1 and x2. Okay, so this will give you the dependency of the constant Cn on x naught to xn. Similarly, so what you observe is C naught is equals to f of x naught. C1 is equals to f of x1 minus f of x naught divided by x1 minus x naught that we have received. So now what we are going to write is this f of x naught as f. To show the dependency, we are writing as with close bracket. So that is also called zeroth divided difference. Now to show the C1 dependency on x1 and x0, we are going to write it as f of x0 comma x1, that is first divided difference for Newton interpolating polynomial. So if you go for the third equation, so what will be, it is C0 plus x1 minus x0 times C1 plus x x2 minus x0 times C1 plus x2 minus x0 times x2 minus x1 times C2 is equals to f of x2. So if you use the previous values, what you will obtain is C2 equals to f of x2 minus f of x0 minus x2 minus x0 times C1. C1 is denoted as f of x0 comma x1 divided by x2 minus x0 times x2 minus x1. So if you rearrange the things, what you are going to get is this is equals to, that you can verify, easy to verify, that f of x1 comma x2 minus f of x0 comma x1 divided by x2 minus x0, that you can verify. Okay, right, and so on. So what we wish to derive is that Cn is equals to f of x0, that is going to be depend on x0 to xn from the previous results. Okay, since C0 is depending on x0, C1 is depending on x0 and x1, C2 is depending on x0 comma x1 comma x2, 3 points. So Cn will be depends on x0 to xn, that we wish to show that this is actually equals to f of x1 x2 and so on xn minus f of x naught to xn minus 1 divided by xn minus x naught. So this we wish to show that, so these are called higher order divided differences. So we wish to show the following, okay, that this formula is actually true. So in that case, then we have the previous results, okay, right. Let Q be another polynomial that interpolates x1, x2 and so on xn. Further, let Pn minus 1 be Newton's interpolating polynomial of degree at most n minus 1 that interpolates n minus 1 that interpolates x naught to xn minus 1. Then Pn of x can be obtained q of x plus x minus xn divided by x naught minus xn time Pn minus 1x minus q of x. So now since Pn minus 1 of xi is equals to q of xi for 1 less than equals to I less than equals to n minus 1. So therefore Pn of xi is equals to yi for 1 less than equals to I less than equals to n minus 1. Now for I equals to 0 and for I equals to n. Now what is Pn of x naught? So if you recall, Pn of x naught, that is equals to q of x naught plus x naught minus xn divided by x naught minus xn time Pn minus 1 x naught minus q of x naught. Now this is equals to q of x naught plus Pn minus 1 of x naught minus q of x naught. So this will get cancelled. And Pn minus 1 of x naught is y naught, since it interpolates x naught as well. Moreover, what is Pn of xn is equals to q of xn plus xn minus xn, that is 0, right? X naught minus xn time Pn minus 1 xn minus q of xn, that is q of xn, and q interpolates xn, right? That is equals to yn. So Pn is an interpolating polynomial which interpolates x naught to xn. Now recall what is P of x. So Pn of x is equals to q of x plus x minus xn divided by x naught minus xn time Pn minus 1x minus q of x. Now what is Cn? Cn is the coefficient of x to the power n in Pn of x. On the left side, and if you compare the coefficient on the right side, what it will be. So on the right side, what will be the coefficient of x to the power n is the coefficient. So qx is an interpolating polynomial of degree at most n minus 1. So there is not contribution for this first term. Okay, the second term has the contribution. Okay, coefficient. So the both sides are identical. So coefficients of x to the power n on both sides. What it will be is xn is this left side is cn, the right side is, you have this x minus xn by x naught minus xn. So x by x naught minus xn, so that should be divided by x naught minus xn. Now the coefficient of here, so coefficient of x to the power n minus 1 here, that is cn minus 1. Okay, and the coefficient of xn minus 1 here, that interpolates the data x1 to xn. So pn minus 1 interpolates the data x0 to xn. So the coefficient of xn minus 1 here, what it will be, that f of x0 to x0 x1 and so on xn minus 1 minus the coefficient of x to the power n minus 1. So this interpolates the data x1 to xn. So that is equals to f of x1 to xn. So this implies this is equals to f of x0 x1 and so on xn minus 1 minus f of x1 x2 and so on xn. Hence the result follows. So these are called higher order divided differences. So this is nth order divided difference. So similarly kth order, so you can write for kth order divided difference. So this is, we have obtained the following formula. So f of x0 to xn is equals to f of x0 to xn minus 1 minus f of x1 to xn divided by x0 minus xn. Yeah, x0 minus xn. Right. So this we are going to use in the Newton's polynomial, interpolating polynomial. Let's find the one example. So what is the Newton form of the interpolating polynomial for the following data? So you have here x0, xi's, and here you have yi's. So if you write p, so this is x0, x1, x2, xc. So you are going to obtain a cubic polynomial. So that is equals to c0 plus c1 x minus x0 plus c2 x minus x0 times x minus x1 plus c3 x minus x0 x minus x1 into x minus x2. So what is c0 is equals to f of x0, that is y0, that is 1. So first zeroth divided difference, c1 is equals to f of x0 comma x1. So that is equals to, if you recall, f of x1 minus f of x0 divided by x1 minus x0. So that is equals to minus 23 minus 1 minus 24 divided by minus 7 minus 5 minus 12. So that is equals to 2. Okay. Similarly, you are going to get the C2. So C2 is equals to f of x0, x1, x2, right? So that is equals to f of, if you use the formula, f of x1, x2 minus f of x0, x1 divided by x2 minus x0. So you need to determine f of x1, x2 is f of x2 minus f of x1 divided by x2 minus x1 minus f of x1 minus f of x0 divided by x1 minus x0 divided by x2 minus x0. So this is equals to f of x2 minus f of x1. So f of x2 is minus 54 and minus minus plus is plus 23. So minus 54 plus 23 divided by x2 minus x1. So minus 6 plus 7 is 1 minus f of x1 minus f of x0. So that is C1 only, that is 2, divide by x2 minus x0, that is minus 6, minus 5 is minus 11. So that is equals to minus 31, right? Minus 31 minus 2. So minus 31 minus 2 by minus 11. So minus 33 by minus 11 is 3. So C2 is 3. So similarly you can go for C3 by using the previous formula. So what you will obtain? The following. So C1 is, C0 is 1, C1 is 2, C2 is 3, and you will obtain C3 is 4. And then fix in the Newton's polynomial, interpolating polynomial. Here C0, this is C1, this is C2, this is C3. Okay, right. So the system can be solved by using forward substitution that we have already known, and we have derived the higher order divided differences which is given by the following form. So the next task is to learn what will be the possible error in polynomial interpolation technique. So that will be our next class job, okay, that we are going to do in the next session. Okay, thank you.